So hi everyone, thanks for coming. Again, thanks to the host for putting this together today. So hopefully there's no fires to start off with. We've got David to take care of that. Today I'm going to be speaking about, I'm Lyle, I'm a lead engineer at loveholidays, and I'm going to be speaking about analyzers in Go. What are they, why we use them, and how we can build ones ourselves. So fundamentally, what's an analyzer? So essentially an analyzer is a way to check your code before you actually execute and compile it. So it kind of gives you that quick feedback loop. It can tell you if there's inherent bugs in the code, it can tell you if there's security vulnerabilities, and it can help you enforce stylistic choices. But the key thing is it gives you that kind of quick feedback loop, so then it reduces the development cycle. So how do we use analyzers at loveholidays? So I'm not sure if anyone's used Golang CI lint. So we use that extensively. It's essentially a linter aggregator, so we run lots of different linters. We're very opinionated, and again, because we've made those choices in Golang CI lint, which then cascade to our CI/CD, it then reduces some of the conversations we have to have at the PR level because it's already enforced those rules. So it reduces the development cycle. So again, GoVet, I'm sure you've all heard of it. It's a static analysis tool that's built into the Go language. It's very opinionated in the sense that it focuses on code correctness, not code style. So it tells you if there's any inherent flaws in your code and tries to pick that up the best it can. Also looking at the source and the README for it, it also focuses on analyzers that don't give they're always correct essentially, don't give false positives or false negatives to avoid kind of analyzer fatigue. And some of the examples we'll go through shortly include shadowing, printf, and nilness. So looking at this code, can anyone kind of tell me what's the bug here and why this code is not working as it should expected? So you declare an outer variable as x, but then you redeclare that inner here, but it's declaring a variable where you're not actually overriding that variable x. So when you then print it, the developer might think they've actually set it as inner, but because it's shadowing the variable here and you're not overwriting it, then you actually print outer x here. So the shadowing analyzing catch up for you. So printf, so the first two examples show you kind of working. So it's basically telling you the name and age, and that's working fine. Pi with 2 decimals working fine, no issues there. But the bottom one, it's highlighting here essentially that you have only included one argument and there's a missing second argument. And then the last example I'm going to go through is nilness. So the first checks if the pointer is nil, and then the second check immediately checks if it's not equal to nil. And this code essentially here is redundant because we've already checked if the pointer is nil, so we'll never kind of enter this branch, and it's kind of dead code, so we'd rather not have that in our code base. So all these are kind of good examples of the analyzers flagging up issues before we actually get to the kind of PR review. So we have all these analyzers, everything's perfect. We shouldn't have any issues with our code, right? So looking at this code, can anyone tell me what's the issue that you might encounter here? What's the potential bug?
If both 1 nil, then it should first if.
So repeat that?
If both 1 nil, it will execute the first if.
In the first if, they're both nil.
The nil comparing to nil is weird, isn't it?
Well, you're comparing, so here the issue with this is you're comparing two pointers. So actually, if it's a basic type an int, and this is one of the bugs I found in our code base, actually we want to do this, where we want to dereference it and compare it, because we want to compare the underlying values. But what we actually did was compare the 2 pointers, and because they're 2 pointer references, then this could be a bug. And I found this in one of our code bases, and it got me a little bit worried. So I could solve the bug, Or I could build, I solved the bug, and I could build an analyzer in Go to tell me, okay, do we have this anywhere else in our code bases? Is this a flaw? So it kind of got me thinking, okay, how would you build an analyzer in Go? And for this, fundamentally, to build an analyzer, you have to take the Go code, the source that you write. It needs to then be transferred to tokens, and then we then need to transfer that to an abstract syntax tree representation, which is kind of a higher level representation of a language. And then from that, we can then run the analysis output. And this is fundamentally how all analyzers work under the hood. And to go kind of a bit more specific in an abstract syntax tree, so we have this code here, which is comparing two values, and if it does, do something. And the abstract syntax tree representation of this is essentially saying, okay, we've got our if statement, and on one side we have a condition, and if it meets these conditions, then we can execute the body, which calls expression do something. So having this knowledge, we can work and try and build ourselves an analyzer. For just kind of going back to this, and for our specific use case here, we basically, and going back to the bug, we need to identify when it's two pointers that are having an equal comparison and when they're basic types, because we want to pick up those issues essentially. So luckily, Go has this Go analysis package, which essentially is a framework for building analyzers. And so all analyzers in GoVet and Golang CI lint use this framework. So if you build one using this framework, you can then actually put that into those tools as well. All you need to do is respect the analyzer type interface, which comes out of the box, and then define a run function, which we'll go into detail. So again, setting it up is pretty straightforward. We just set up the kind of standard name, what it does, document. We also include this inspect.analyzer, which I won't go into much detail here, but essentially goes through the abstract syntax tree in a much more efficient manner than different transversals. And then here you can see we define the run function, which we'll look at next. So with the run, and kind of going back to our example, and as we said, we need to basically figure out, is it a binary expression? Is it comparing two pointers, and are they two basic types? And here, using the inspect.analyzer framework, we can use this function, which is called preorder, which filters out the nodes. We can just filter for all the nodes in the abstract syntax tree that are a binary expression, and then apply our logic to it to see if it meets the requirements for the code we want to check. So when we run the preorder, which again is the kind of more efficient algorithm for transversing the abstract syntax tree, it will first filter out all the binary expressions, and the first thing we need to do once that's done is check, okay, cast this to a binary expression, and if it's not a binary expression, then we return that. And then the next stage is to check, okay, is it a binary expression operator, and is it a comparison operator? And if it is, then we can do the next check, which is checking the pointer comparisons, which I'll go into detail here. And this is kind of the crux of what's left, essentially. And we're getting the left and right type from the binary expression. We're seeing if they're a basic type. So Go has this concept of basic types, which are essentially integers, floats, strings, etc. And if it is, we're then able to add a diagnostic to this path to say, okay, we're comparing pointers to basic types with the left type and right type of what they are, and then pass that back up to the user to then inform them what to do. And so kind of going back, so we've defined our pointer analyzer, and so we defined the run function, which is there. There. And so now what we can do is we can build that pointer analyzer. Above here, which I haven't included the code, is another set of code that will go through all the packages in that Go source code, so it'll load each one. So you can then run through them all and run the analyzer on each package. And then once that's done, So once you run the diagnostics on that package, you can then add the message for the user to use later on, which says, okay, I found an issue here because you're comparing two basic pointer types in this file name, in this line, and in this column with the message. And then once that's done, you can then return it to the user. So going back to the original issue we had, so it should flag up here. Okay, now it should flag up essentially we are comparing two pointer types, and we're not dereferencing because they're two pointer types and they're two basic types, so we want to flag that up to the user and tell them. So we run this tool, it now prints out the file name here with the comparing pointer types to basic types, which is great. So we've essentially, in a few lines of code, we built an analyzer which is kind of useful, and I was able to run this through the code that I had in terms of our code base to check if there are any other issues. There wasn't any other issues, it was just that line of code, so it was a good thought experiment. So next steps, so we've built that analyzer. We can now, as I talked about before, we can integrate that with Golang CI lints, and I think the process for this, which I've not gone through, I think it's just basically pulling a PR, that getting accepted by Golang CI lint, and then you're then able to select that linter in your set of linters. With GoVet, it's slightly different. Obviously, it's part of the Go code base, very strict requirements. You'd have to find something that's fundamentally wrong with the language for it to make it in there. Cool, so, and then a kind of last closing point as well is going back to this code. Obviously, for us, there's a conversation we had as a team why this code was in there, why we were comparing two pointers in the first place, or why we represented those basic types as two pointers. This actually might be, somebody might want to actually do this check, so maybe analyzer's not useful for them, maybe it shouldn't be done in another code base, so it is useful. Again, I think this use case is debatable, but again, it was just an interesting thought experiment to run through and build. And yeah, so with kind of learning all of this, I've spent a lot of time in my spare time, very interesting, writing compilers or learning about how to build compilers. And it's great because these are two great books that I really recommend, but it's great because it's allowed me to kind of look at the Go source code and understand it at a much deeper level, and then kind of wrap my head around analyzers and kind of how they work. And so if anyone's interested in this, then I really recommend these two books because they're both great. That's it, and if you want to see the code, it's there to have a look at, and yeah, great, thank you very much.